Hi everyone, welcome to episode 18 of the Aspiring STEM Geek. In this episode, I talk with Dr. Damian Handzy. We talk about physics, finance, and how the two are intertwined. We talk about how Damian became interested in math and science as a child, his decision to study physics for his undergraduate at the University of Pennsylvania, his PhD thesis in nuclear experimental physics, his pivot from nuclear physics to finance, financial risk, and behavioral economics. Towards the end of the episode, we talk about complex systems and how they are applied in places such as financial markets. I hope you enjoy. Dr. Damian Handzy, thank you for coming on.
My pleasure, Adrian. Good to be here.
So, as always, I try to bring a gift for the live events. Here you go.
Thank you very much. I'm looking. Oh, from New Mexico.
Yeah. Awesome. So, was in the area, and this has piña nuts in it. So, I hope you enjoy.
Okay. All right.
It has a good flavor.
We may get to my travels to Santa Fe.
Okay.
The topic might actually come up towards the end.
Okay. Awesome. And yeah, thank you for this. We'll talk about books, but you happen to have an extra copy of Skin in the Game by Nassim Taleb, and I actually wanted to bring him up in the book section as well. So that's awesome as well. And I have not read Skin in the Game yet, so thank you. But
all right,
let us start from the beginning. Growing up, were you interested in science and math?
Yeah, so I'll say I was really lucky. I grew up in a house where my dad. So I was born in Minneapolis. My dad was in grad school, either for math or physics at the time. He wasn't sure which. In the first year at the University of Minnesota, apparently back in '68, you didn't need to decide. So he was studying both.
Interesting.
And so when I was 10, he actually decided he was working as a programmer on Wall Street for a bank that's now owned by Bank of New York. He quit. And I remember I was in fourth grade. He came through the door and announced that he quit his job. He's going to medical school, and we're all moving to Mexico. My mom was a psychologist.
Okay.
My dad was a mathematician, physicist, turned physician. And in Mexico, I didn't speak Spanish when I got there. I didn't understand anything on the television. We didn't have a telephone. This is long before the internet existed. I read his medical school books. And when I got to the equations in the biochemistry book, so I'm 11 years old, he was teaching me logarithms. So I was really, really fortunate.
Yeah, I was not that advanced at 11.
Look, I was bored to tears, right? I studied anatomy, right? I memorized every bone, every muscle, the names of the bones, the muscles. What can an 11-year-old understand, right? But it got me hooked on math and science. I will say that because I've heard the comment, oh, kind of math came easy to you. Math, yeah, this was natural for you. I object to that notion with every fiber I have. Just because someone has a tendency towards studying something doesn't mean that they don't work their butt off to understand it as well as they can. So while it's true, I had every advantage because my dad taught me math really early and really well, I also had to work at it. And what I mean is, my freshman year of high school, I got a C+ in algebra. My dad read me the Riot Act. Here he was in his late 30s at that point. And he's like, Damian, you see how hard I have to work to catch. I had to go to medical school in Mexico because I couldn't get into an American medical school because my college grades were so bad, because my high school grades were so bad. He said, don't goof off. Work at it now. Learn it now so you don't have to learn it when you're 37. And that put me on a trajectory to really studying this stuff.
That's great to hear. And a good takeaway is boredom is a great motivator. So
yeah,
fine.
It can be.
Yeah. So it's tougher nowadays given all the stimulation that we have. And I very much agree with you on the math portion. I'm very self-conscious about my math abilities. It took me a while to get comfortable with a lot of it, just even calculus and things like that.
It should take you a while. There's a My dad always described it as mathematical maturity. And he said, you're going to learn a topic, you're not going to understand it for a year. Right? You might be able to do mechanics of math, right? The mechanics of algebra, or it's memorization, it's routines. Really understanding what you're doing takes a long, long time.
Yeah. Yeah. Fully agree with both those things. So great to have such a household that focused on academics. For your undergraduate, you went to pre-med. That it kind of makes sense that given your background, and now I kind of see the inverse of what your father did is you were thinking about pre-med, but then you went to mathematics and physics. Can you talk about what motivated that?
Sure. So, Matt, I mean, look, I realized I was following my dad's footsteps for, I was old enough to watch him go to med school. I was old enough to understand, the risks, not really understand, but I could at least appreciate the risks he was taking, et cetera. Anyway, med school was the natural thing for me to start off with. It was the first semester of my sophomore year when I had a professor who just blew my mind. She taught, first of all, she looked like my grandmother, which... my grandmother had a third grade level of education, really, immigrant to the U.S.
What was this professor's name?
Faye Eisenberg-Selov.
Okay.
In fact, the F meson is named after her, the Phaon.
Okay.
She first day of second semester physics class, she had us write on the blackboard all the equations we could remember from the previous year. Just whatever you could for the first 40 minutes. And then she went up and she erased almost all of it. She left like 5 or 6, maybe 7 equations. And she said, "Now realize this is the state of physics. What you learned last year was physics up to about 1900. So everything on the board is what physicists knew in 1900. And she erased most of it, and she left, like I said, 5, 6, maybe 7 equations, and she started manipulating them, and out pops E equals mc squared. Oh my God. We could have derived Einstein's most famous equation knowing what we knew last year. That was just the start of how she presented stuff to us. Brilliant, brilliant teacher. She taught me relativity. She taught me intro to quantum mechanics, modern physics. The Young double-slit experiment, where you learn that an electron, if you have 2 holes in the screen and you shine light on it, we all know light goes through both holes. We think that's natural. But if you shine electrons at it, we think, oh, well, electrons are little balls, right? I always thought of them as little silver balls for whatever reason, whatever. And it's going to go through either this hole or through this hole. So nonsense. They actually go through both holes. This is the wave-particle duality. And so here I am being introduced to this, and I'm fighting it with all my fire. It's like, no. And we're trying different thought experiments and, what if this, what if that? And finally, she says, look, I'm glad you're struggling with this. Everyone does. You have to accept that this is reality. When the data tells you that your preconceived notions don't conform with how nature behaves, you have 2 choices. You can keep fighting, you're going to lose, or you can say, I'm wrong. I have to accept this. Abandon your preconceived notions, no matter how deeply you hold them. And that lesson changed my life. And I really do mean that. That philosophy, that's not a physics lesson, that's a life lesson. If the data tell you you're wrong, change your belief.
Yeah.
That applies to everything.
And we'll talk about a variety of things, behavioral economics, things like that.
Yep.
It is tough for us as humans to admit that we're wrong, and I get it.
Yep, 100%. Getting comfortable with being uncomfortable, I think, is the single most important thing that kind of process taught me. So I abandoned, first of all, I wasn't really interested in biology. Chemistry, I found to be a derivative of physics. I was wrong. It's not. Okay, but the 19-year-old brain that I had told me otherwise. And so I said, I want to study the thing, that I want to understand how the universe works. I have the opportunity to do that. Let me go do that. So physics became it.
Okay. So in undergraduate, did you decide you wanted to get into nuclear at that point, or?
Yeah. So I was really lucky. So Penn had a vibrant program in what we then called solid state.
Okay.
It's now called condensed matter. I was trying to remember the name. It's been a little while. We had a solid state program, we had a nuclear program, and we had a high energy program. Now the laboratory, there were condensed matter, solid state laboratories in the building. There was a nuclear accelerator, low power nuclear accelerator on campus. The high energy physicists did all their work in other labs, but the theorists were there. So I got to taste the three flavors of physics. And what I realized was solid state, condensed matter, it's a team of one or two people. It's solitary work. High energy physics, it was a team of 400 people. So a grad student in high energy got to be responsible for detectors number 312 through 322. Not exactly, but nuclear was teams of 5, maybe 10, maybe 15 people, and you could understand everything about it, the motivation of the experiments, the theory behind it, the measurement, the publication, the analysis, and that's why I chose nuclear, because I could get my hands around the whole thing and I could learn it from soup to nuts. And it was incredibly interesting to try to understand how this damn little itty bitty thing works.
Okay. So somewhere in between your sophomore and junior year, you had a summer research internship at Indiana University of Bloomington.
Yeah.
Was that nuclear related?
It was, yeah.
Okay.
Yeah. So the National Science Foundation sponsored scholarships in the summer, and I was lucky enough to get into that. So I spent, I think it was 10 weeks in Bloomington. They then, at the time, they had a cyclotron facility, so an accelerator. I actually don't remember what species of nuclei it accelerated. The project I was working on was a feasibility study to measure the mass of a neutrino. Now, back then, they did not yet know, we didn't know whether or not neutrinos had mass. And there was a muon capture technique. So this is going to sound strange. You've got a high energy ring of, I think it was electrons, a high energy ring that you cool down. So what does that mean? How do you cool down a high energy ring? Well, remember, temperature is actually a relative measure of the relative speed of one object versus another. So high temperature gas means, they're all zipping around, right? If they're not all zipping with respect to each other, if they're all kind of stationary with respect to each other, but they're still moving very, very fast around a curve, that's low temperature because they're not bouncing around each other. So they're all kind of doing the same thing. They're flying at high speed, but they're all kind of doing the same thing. So condensed low temperature allowed you to capture, it was actually muons, and the decay into a neutrino. We wanted to measure, and certain properties of this, we were able to study whether or not it was sensitive enough to measure the mass of a neutrino.
Okay. That sounds really interesting.
It was fascinating.
Yeah. So I guess that I have to say, I'm a statistician.
Yeah.
Not a physicist. So for the summer research internship, seems like that's what kind of led you towards your PhD thesis down the line.
It convinced me I wanted to do nuclear.
Okay.
It didn't point to the actual thesis I did in grad school. The topic, my thesis topic and that summer internship topic were independent of one another.
Okay.
One didn't imply, one had nothing to do with the other, but the program taught me, I like being around smart people. I shortly after that, maybe 10 years later, someone told me something that I still tell my kids, and to this day. You never want to be in a room where you're the smartest person. You never want to be in a room where you're the dumbest person. You always want to be in the middle. And my version of that is I always want to have people I can learn from, and I always want to have people who I can help learn. And that experience said, going to nuclear.
That's a good philosophy. Okay, awesome. So you finished your undergraduate at University of Pennsylvania.
Yep.
And you had the choice of pursuing a graduate degree at either Massachusetts Institute of Technology, better known as MIT, or Michigan State University. Why did you choose to do your PhD at Michigan State?
So I went around to every physicist in the department at Penn asking, where should I go to grad school? I want to do nuclear. I want to do nuclear experimentation. So not theory. I want a hands-on experiment. Where should I go? And I got a variety. As a statistician, you'll appreciate, I had a distribution of answers. Several professors said, oh, go to school X. Turns out that's where they went. Okay, irrelevant. There were two schools at the top of the list, MIT and Michigan State. And I was like, okay, MIT I get, right? Its reputation is, it's the best damn school. It's the best STEM school in the world, right? Arguably. It's definitely in the top 5, right? Okay. Michigan State. Why would I go to Michigan State? And one professor explained it really well. So, Damian, if you want to do nuclear physics, if you want to do nuclear experimentation, there is no question you go to Michigan State. He said, if you want to do anything else, go to MIT. So, okay, that's interesting. Help me understand that. He said, look, MIT on your resume is going to open doors for you. Michigan State will not be able to do that. If you want to do other things in nuclear, he said, but Michigan State's cyclotron, it was the world's only superconducting cyclotron facility. He said that school produces more top physics papers, journal articles, peer-reviewed articles than like the next 10 schools combined. He said, MIT will have the best students, he said. Michigan State will have the best professors. Yeah. Do you want to be a good student or do you want to be a good professor? So, okay, this is a no-brainer. I was 100% nuclear physics. That's what I want to do with my life. So there was no question. I went to Michigan State. And the best physicists on the planet were going there.
Okay, interesting. So your PhD program was focused on experimental nuclear physics.
Yep.
The timeline is interesting because you were in the program from 1991 to 1995.
Yep.
From my understanding, talking to nuclear engineers and scientists, this was a nuclear winter for the field, to make a bad pun, but in the 1970s, you had organizations like Greenpeace campaigning against nuclear energy in general, not just defense. Chernobyl disaster in 1986, fiscal austerity in the 1990s after the fall of the Soviet Union. Given all these headwinds, what motivated you to, or did that factor in at all when you were thinking about this?
It didn't factor in at all, and it actually didn't impact this field. So what you're talking about is applied nuclear engineering. I wanted to have nothing to do with nuclear weapons. Nuclear energy, that was not what I wanted to, that was the applied side. So the Greenpeace, the anti-nuclear movement, it was almost irrelevant, right? I was studying how the nucleus behaves, not for the purposes of producing energy, not for the purposes of the purpose was to understand how the nucleus behaves. And I chose, so I already explained why I chose it from a team perspective, right? Size of team. The topic, so atomic physics was pretty well understood by that point. Now, material science obviously has taken off, right? But it was too applied for me. I was too theoretical at the time. I didn't want applied stuff. Nuclear, so you can't apply statistics to a system that has 50 participants. Right? Just not enough. You're not going to get enough. It's not gases and solids. You could apply statistics to because you've got a lot of electrons. You got billions. You got Avogadro's number of electrons moving around. That's not what you have in a nuclear. The nuclear reactions that I was studying were non-statistical. They were quantum mechanical, therefore very difficult to predict their behavior, strongly interacting at the edge of stability, meaning just enough energy where you're breaking them apart, but you're not vaporizing them. So you're probing how the nucleus behaves as a thing by attempting to break it up. So actually, it wasn't a nuclear winter from the academic, pure research perspective.
And this is the foundational science, and we'll talk more about what that means and why it's so important.
Yep.
Okay. Not a physicist or an expert in nuclear, but I want to try to get into your PhD thesis.
Yeah.
I attempted to rephrase the title to make it a little bit more digestible to the layman like myself. So we have using proton pairs to measure the size and duration of argon-scandium nuclear collisions at 3 different speeds. My understanding is the argon nuclei were accelerated into the stationary scandium target. What is the motivation of the experiment?
So this was one of many experiments that the lab did to study how nuclei behaved. So let me take a step back, because I actually think it's a fascinating kind of conundrum. When I first got introduced to nuclear as a topic, right, someone said, okay, Damian, this is an interesting question. It's an interesting topic you're getting into. Do you know why the helium nucleus exists? I said, what do you mean? He said, well, you got 2 protons and 2 neutrons sitting right next to each other. The protons are pushing against each other. They're both positively charged. We know that 2 positively charged particles will fly apart because that's what electricity does. Neutrons are neutral. They're not doing anything. So you got these 4 things sitting right next to each other, and it's not flying apart. How does it exist? How does anything heavier than helium, which is just 1 proton and a neutron, or a couple of neutrons, how does anything heavier than hydrogen exist? I had no answer to that. There must be a force stronger than the repulsion of electricity that holds it together. That force, the nuclear force, this is what's responsible. When you break that's the amount of energy that's released in a nuclear explosion, because it's so much stronger than electricity, orders of magnitude stronger than electricity. Now, when you start adding more and more protons and neutrons, you get so when I say strongly interacting, I mean the strong force is responsible for this. The strong force is bizarre. It's bizarre. Electricity and gravity extend in space infinitely. The formula is 1/r² for their strength, right? Gravity drops off. If you double the distance from an object, your gravity is 1/4 what it was, right? It goes to the square of the distance. Same thing with electricity. The strong force, it only extends about the size of a proton away from a proton. So if you've got 2 protons that are separated by approximately their own radius, maybe it's twice the radius. It's been a long time. I don't remember the exact details. But when you separate, so imagine these two things separated by about that far apart. They're now pushing each other far and farther apart. But when they get close enough, they fuse together. Holy crap, that's kind of cool. The math of that is fascinating. So, okay, now you have this bag of these protons and neutrons in this thing. You got another bag over here. You're going to collide one into the other to study how this bag works. If you do it really, really slowly, boom, and they just kind of go off and they get excited, they vibrate, if you do it too fast, you're going to vaporize the whole thing. That's a completely different field. That's fascinating. That's really high energy stuff, right? So relativistic speeds, near the speed of light, you smash them into each other, and you actually get protons and neutrons breaking into their constituent parts. They've just recreated, like literally in the last 5-10 years, and they just published just very recently, results that mimic the conditions immediately after the Big Bang.
Large Hadron Collider?
Actually, no, this was done at RHIC, the Relativistic Heavy Ion Collider in Brookhaven, out on Long Island.
Okay.
But the Large Hadron Collider also did stuff like that, right? In this case, you've got heavy ions where you're smashing them together at RHIC. I don't remember what the heaviest species that CERN. The Large Hadron Collider. That was a thing in Texas that didn't. That is that right? It's been so long. I forget which lab was doing what. CERN, the European Center for Nuclear Research, is the higher energy. RHIC out on Long Island is the one that can do the heavier ions.
Okay.
So, but back to what I was doing. So you don't want to vaporize it. You don't want to just have them bounce off. You want to collide them with enough oomph, with enough energy that they will break into pieces. Right? Maybe an alpha particle comes out, so a helium nucleus. Maybe a boron nucleus comes out. Maybe a big chunk comes out, and in the process, sometimes you're going to get just 2 individual protons coming out. That's what I was studying. So I was using the protons as a probe for what this thing does. And here's what I mean. If the source from which these protons are emitted is really, really big, if somehow, it collides, it expands, and then it emits protons, and one is emitted from one side on average, the other one on the other side, they're not going to interact with each other as they fly away very much because they're far apart. If they come from a much smaller source, they're going to get pushed apart more. And so you're going to so by the time they get to your detector, they're going kind of in opposite directions. These two might still be going in the same direction. So statistically, you can measure properties of this blob based on the two protons that come out. You can't do it on one. You have to have two coming out. And there's also nuclear effects. There's a resonance effect at a particular relative momentum between the two that allows you that resonance, it's a nuclear resonance, part of the strong force. That nuclear resonance allows you to probe the space size, meaning how big it is for how long, really, really well. So we were able to pinpoint how much of this energy goes into breaking things apart. We even probe kind of what shape it takes, because is it a blob? Is it more like a hockey puck? And there were actually some theories that came out that said it's going to actually look like a donut. Now that shocked us, because what it says is, imagine you have two things head-on collision, right? Boom, bowling ball on bowling ball. Boom. And it's going to crack into all these pieces. Well, the blob that you expect it's going to still be kind of central, right? You're going to have stuff in the middle, you're going to have stuff on the outside. Now imagine if I told you these two things collide and the result is a donut shaped like this, where there's zero probability of anything being in the middle. But the middle is the most likely place. So it was a fascinating kind of combination of theory and experiment.
So in terms of the model that you were just talking about, is that the Boltzmann-Uhlenbeck transport model, the BUUT model that's better known? So it was modeling this donut shape after the collision, but you found something different, isn't that correct? So what did your actual results, how did they differ, if at all, from the model?
So ultimately, our data and our device didn't have the resolution to decide to measure whether or not a donut hole existed. So we could not tell the difference between a hockey puck shaped object and a donut shaped object. That was just resolution of the apparatus that we had. But ultimately, that was kind of a detour on my thesis. The theory predicted it. We couldn't measure whether it was true or not. And but we did establish the sensitivity at different speeds. So we actually so my predecessor, who's now a professor at Ohio State and works at RIC, he did it at a lower energy, same exact argon on scandium. And yes, the argon atoms, the argon nuclei were accelerated into a foil, basically like tinfoil, but scandium foil. And that was the collision. Same exact species at three different energies or three different speeds. I did the middle energy and the higher energy. And we established a pattern of kind of how small or big that source was, and how much excitement went into the system to better understand stuff. But the theory, the theory that this is how all science works, right? There's a theory to understand how the system behaves, and then you do experiments to either measure attributes of the theory, probe the validity of the theory, or discover, maybe the theory is completely off, right? And so you're always comparing to something, to some model.
Makes sense. You got to work with pretty high-tech instruments during this research. Yeah. Can you talk about the hodoscope particle detector, the K12,000, superconducting cyclotron, and the MSU-4 array? What are these instruments and how do you use them?
So the superconducting cyclotron at Michigan State, this is why I went there. So superconducting meant it could be much, much smaller than a typical synchrotron. So it was physically actually about the size of the room a little bit bigger than the size of the room that we're in. And it was invented, an immediate practical application was in medical research. Michigan State built one for research purposes. So it's the thing that accelerated the nuclei, right? So the energies that it could accelerate. So the energies that I did my experiment at. So argon accelerated up to 120 million electron volts per nucleon. So every nucleon, proton, neutron in the nucleus had 120 MeV. Just to give you perspective, the mass energy equals mc squared. The mass energy, so the amount of mass equivalent, a proton has a mass of 938 MeV. So call it 1,000. Okay? And my experiment was being run at 100. So it's 1/10 the energy that it takes to create the proton. And so that gives you a reference frame for how much. I don't recall the speed, right? So was this at 0.99 C, 0.98 C, 0.95? I don't recall. We don't think of it that way. We think of it in terms of energy. So we never really quoted the speed, but it's relativistic speeds, meaning relativity plays a role. In other words, so the ball in the laboratory frame, when the ball hits the tinfoil, so the tinfoil is a bunch of balls, right? The nuclei are a bunch of balls, but the ball coming in, because it's moving so fast, it's actually squished. So one of the effects of relativity is distance gets contracted. So things seem like they're smaller in the direction of motion. And so this ball is actually more like, it's not like a pancake. It's not that thin, but it's kind of smushed down. And you got to take those method, the equations of that, you got to take that into account. Anyway, back to the device. So the device sends these very, very fast moving nuclei down a vacuum tube. So it's a pipe in vacuum. And in a vacuum, we have a detector. So you're going to collide them. Stuff's going to come out. You got to catch the stuff that's coming out. The 4-pi array, wonderfully named, because the surface area of a sphere, the same way that kind of everyone knows that the formula for the circumference of the circle is 2 pi r. The area is pi r squared. The surface area of the sphere is 4 pi r squared.
Okay.
So take out the r squared. That just tells you how big the thing is. 4 pi is the amount of angle that surrounds something. So if you can see in 4 pi, you're capturing everything. So the idea is that this 4 pi detector had eyes all around the target. Now, obviously, there's a beam coming in. Most of the beam comes out. So you're not going to catch the very, very small bits. You can't look from this perspective, but from everywhere else, you can look at it. So the 4 pi was catching all the stuff that came out. We took one of the modules of the 4 pi, removed it, and we put this hodoscope in. Now, the hodoscope had 56 very, very high angular resolution individual detectors. And this is where we caught the protons. So if the protons flew, in a given collision, protons are going to fly everywhere. If they flew into our hodoscope, we caught them, and we said, here's a proton, here's a proton. And from that same collision, what else came out? The 4 pi detector caught all the rest of the stuff. So in a given collision, we got all this stuff flying out. We're catching all of the big chunks in the, I'll say, low resolution 4 pi device. We're catching the protons in the high resolution hodoscope. So we can say, in this collision, 2 protons came out. And by measuring how much rest of the stuff come out, we could determine actually whether it was a head-on collision, a glancing collision, or how far in between. So we could actually then say, because in a head-on collision, the source of the proton should be big. In a glancing collision, only a small portion of the 2 circles, right, overlap. And so the source where the energy is should be very small. So in a glancing collision, you should have protons flying out farther apart because they're coming from a smaller source. And in a head-on collision, they should be more this way. And that's exactly what we saw.
It's awesome. So you said earlier that this is more fundamental research rather than applied. So can you explain why fundamental research in general is so important?
Sure. I'll give two my two favorite examples, and I love this question, right? Because I actually think fundamental research is one of the most important things that humans do. Now, I think fundamental research is the most important thing that humans do. Let me go that far. Here's what I mean. So my best example is, I think it was in the 1880s. I didn't look it up before this. J.J. Thomson playing around in his laboratory with these tracks in gas tubes, and he's seeing these things that are flying through here, and the man discovered the electron. That was 150, now 30, 40 some years ago. The electron is discovered. The lights in this room, the cameras, the internet that people are watching this through, all of that is because somebody was curious about what these little tracks are in this gas tube 150 years ago.
Worked out well for us.
That should case closed.
Yeah.
Right. I rest my case. It's what if no one had done that, the entire world economy, we would still be in the 1880s. Right. We'd have locomotives. We wouldn't have airplanes. Right. We wouldn't have computers, and we'd have airplanes. We'd have mechanical airplanes. Right. But you know what I mean, right?
Yeah.
It's fundamental, and I mean it's helped. It's helped everything from health, to travel, to economics, to yeah. So that's my best example.
That's fantastic answer. So
sorry, 99.9% of fundamental research does not result in we can do something about it, but the 0.1% that does. And I'll be exaggerating. It's probably 95% of fundamental research doesn't actually have an eventual application. But just like a private equity portfolio, right? You take 100 bets, you only need one or two of them to pay off at 10x, 20x, and they fund all the rest.
Yeah,
that's the game that this is playing, right? It's a statistics game. There's a power law distribution here, not a Gaussian distribution, where you have enormous overrepresentation by a small number of events that they pay for everything else. And that's what fundamental research does for humanity.
Yeah. And earlier you mentioned off camera, the ensemble of knowledge is very valuable too.
Absolutely. And the training, right? So you've got people who are trained in how to really determine what's true and what's not, which is an incredibly difficult thing for humans to do. I was absolutely fascinated in grad school by, we're going to get to this in a moment, what turned out to be a lifelong study and an appreciation for neuroscience and behavioral economics. In grad school, here I am watching these physicists, these world-class physicists who had to really think hard about statistics problems. They had to work through, and wait, that's not how you do this, and I got to pull this result, this. And it would take them not hours, not days, weeks, months to work out a new problem and they had to satisfy each other that they had worked it out correctly. Meanwhile, I'm watching my dad in an emergency room who immediately knows the answers to the tricky questions that he has to face, right? And lawyers, similar thing, right? Business people, similar thing. There isn't a cognitive bias against the field that they're working in. In science, there is. Right? We want a certain result to be true. We have to fight like hell to be intellectually honest. Right? That training is phenomenal for other fields as well.
Yeah. Speaking of other fields, you did have a pivot. So you were studying nuclear physics. You had your undergrad in physics and math. Then you pivoted into the world of finance. So what motivated this change in fields?
So there were a couple of things. Being a physics student was awesome. You're paid very, very little, so it's painful, very painful. But I had the privilege of working on really, really hard problems. I was learning an enormous amount. I was only working with very, very smart people. There were a lot of side benefits. There were a lot of perks, right? I got to work. I got to meet some brilliant, fascinating people working on hard problems. However, what I saw was professional physics was not life being a student. Professors spent an inordinate amount of time on research grants, on administrative duties, and I didn't want to spend 70% of my time not doing science. I wanted to do science. That job doesn't exist. I concluded. And I said, okay, not only that, I didn't want to live in the Midwest. My family's from the New York area. I wanted to come back to the New York area. There's not a lot of physics research going on in the New York area. I mentioned Rick. Okay, that is true. So I left for a couple of different reasons. Now, I'll also say in my second year of grad school, I remember a fellow grad student walking around with a copy of the Wall Street Journal under his arm, and I berated him. I just made fun of it. That's just man-made. There's nothing intellectually interesting about that. That is such a boring topic. How can you even read that? 2 years later, here I was applying to Wall Street firms. So the pivot was real. I decided, look, I had a skill set in programming, because physicists have to program all of the analysis that you're doing, data collection, analysis, quantitative analysis, presentation of the results in written form and verbal forms. You have to give presentations. Back then, it was actually with slides. I mean physical slides. I don't mean PowerPoint. I mean slides. Right. So there was an array of skills that I had, and I went back to the fact that, hey, I like working in teams of 5 to 15 people, and I did a lot of research, read a lot of stuff, talked to a lot of people, and I decided on Deloitte and Touche as consulting. I said, I don't know business, so I said, let me get my bearings, and I went to a consulting firm to understand the world of business.
Okay, great. And obviously, I worked a little bit in finance, so I'm definitely a little bit more comfortable with some of these questions and lots of applied statistics here. So in 1999, you founded the financial technology company called Investor Analytics.
Yeah.
The company provided risk analytics for hedge funds. Can we first define what risk is within finance? So I think a lot of people may equate risk to standard deviation of the returns of an asset or the left tail of a distribution for an asset.
Yep.
So, but it's more complicated than that. So how would you define it or give an explanation of risk?
So Einstein's famously known for saying, make everything as simple as possible, but not simpler. And defining risk as volatility or volatility as risk violates Einstein's principle. That is an oversimplification. Full stop.
And volatility would be something like the standard deviation.
Standard deviation, right. Okay, so just invoking standard deviation has an enormous number of assumptions built into it. You assume normal distribution. Stocks are not normally distributed. It would be wonderful if they were, because we could do the math. And that is why we use a normal distribution in finance. So financial analysis, I will say, fails the intellectual honesty test that fundamental research applies. I've got a friend at MIT, an economist named Andrew Lo, who is famous for saying, physics has 3 laws that explain 99% of observed phenomena. We economists, we have 99 laws that explain 3% of what we see. And while, okay, tongue-in-cheek, clever, and he's a very clever man, right? I quote it because he is onto something deep there. The normal distribution does not apply to stocks. So why do we use it? Because we have nothing else that we can use. Oh, so that's kind of like saying medicine, you're ill because your humors are out of balance. But humors don't have much to do with human biology. That's okay. We don't have any other theory, so we're going to use this. Huh? What? Okay. So volatility, standard deviation, is a measure of the width of a distribution when you apply an assumption of normality, of a Gaussian distribution on it. So the Gaussian distribution fails. It doesn't fail 95% of the time. It does describe the peak of the distribution rather accurately. And I've studied this, right? and investor analytics, we did a lot of research on what models to apply and what not. And I have a bunch of slides that show 95% of the time, it actually works really friggin' well. It's in the tails that it fails miserably.
And when we're talking about tails for asset returns, it's going to be extreme positive returns and extreme negative returns.
And by extreme, we mean, so it works to about 2 standard deviations, which is about 2% up days, 2% down days. Now, what I've explained in layman's terms, what I've explained is thinking that a standard deviation is risk is like saying full breathing, full inhale, exhale is risky. Okay, what do I mean? A portfolio will be up 0.5%, it'll be down 0.5%. It'll be up 0.75%, it'll be down 0.75%. 68% of the time, approximately, it's called 70% of the time, 7 times out of 10, it's going to move by 1% up or down every day. Every day. That's normal. That's what it does. That's not risk. That's not risk. That's what it does. When it moves more than that, they start saying, oh, now that's risk. Okay. From a qualitative perspective, that's perfectly fine. The problem is when you start quantifying it. So, okay, how much risk is there in the portfolio? What is the probability? This is where we get in trouble. What is the probability of a down 3% day, a down 5% day? According to the normal distribution, it's so small, don't even worry about it. It's a 1 in 1,000-year flood, except they happen every other year. In medicine, that would be called malpractice. In the medieval ages, an architect who built something that collapsed was executed. Somehow this passes for standard operating procedure on Wall Street. It's awful. It's wrong. It's just wrong. And yet we all do it because we have nothing else. So that's my starting point for kind of, now we've got lots of more sophisticated theories about how the tails of the distribution work and what is risky and what's not. But even something like, the global financial crisis. So that was all around credit risk. 3-5 years before that, we started at Investor Analytics, we started looking at credit risk, and we said, okay, everyone uses credit ratings. So the big three, Moody's, S&P, and Fitch at the time, did credit rating of various bonds. So we wanted to look at what is the relationship, what's the correlation between credit ratings and probabilities of default, because that's the risk that you have of the bond, is that the issuer is not going to be able to pay back the money. And we were shocked. There was almost no correlation. Okay, so a BBB rated bond does not default that much more often than a AAA rated bond? Correct. So we can't use this as a basis of a credit model. That's what we concluded. And we didn't. Our clients were asking us for one. We said, well, we can't use that. So we went and researched other stuff. Meanwhile, our competitors built a model off of credit rating because everyone assumed that it would work. And they built the model. They made millions of dollars doing that. And I remember speaking with one of the designers of one of those models at a conference long after the global financial crisis saying, hey, this is what we found. We found that you really couldn't use credit rating. And we're at this conference, we're 3 drinks in, and he turns to me and says, Damian, we found the same thing. You've got to be kidding me.
Medical malpractice.
Yeah. Fiduciary malpractice. Except they were fiduciaries, so there's no malpractice.
Yeah. Another sticky issue within the field. So I worked in finance for about 4 years. I had a chance to see many hedge fund strategies and the ways that their assets were marked. Some of these strategies were very opaque. And even if you were an investor, you didn't get to see the underlying performance of the assets. So the individual assets that make up the portfolio. Given that your firm focused on hedge funds, how do you deal with this?
So the opacity, okay, so first of all, if the hedge fund were our client, we had full transparency into what they were trading pretty much every day. At the end of the day, we would collect their entire book from their broker, from their administrator. That's a firm that does the math, the daily value calculations. And we would collect those holdings. And then we would overnight, we would do a risk assessment, scenario assessment, probability assessment, et cetera, et cetera. So there really was no problem with transparency if the hedge fund were our client. The problem came in when the investor into the hedge fund was our client. So let's say a pension fund, right? Or some other institutional investor investing in 10 or 20 different hedge funds, or a fund of fund investing in multiple hedge funds. Now, it's not, the entity that is doing the trading doesn't have a good reason to send us the holdings. So we had to cajole, we had to beg, we had to not borrow. Well, we invented ways to borrow. And the investor could put pressure on the hedge fund. Typically, the smaller hedge funds would do that. They would reveal the holdings. The larger hedge funds said, no, you're going to trust us. There's an opacity. Sorry, there's a perceived kind of mysticism to hedge funds. We're smarter than that guy over there. We have secret sauce. We know what we're doing. Look at the returns we've posted. We've made our investors, 10%, 15% per year. Trust us. We're going to do the same for you. We're not going to tell you what our secret sauce is because that's we can't do that. We can't reveal our secret sauce. And a lot of people bought into that. So we invented ways of synthesizing transparency, if you will. Statistical regressions of their returns against what they said they should be holding. And that works a little bit. It's better than nothing. It's not quite reading tea leaves, but you've really got to be really good at understanding what you're looking at in order to interpret it well. So back to the MIT professor that I mentioned before, we actually had a collaboration with him where he came up with a way to discern friction in marketplace. So he did a research study that he showed that when you have autocorrelated returns, so a fund, every month the fund is posting, this is how much we made this month, this month, this month, this month, this month, and you look at those returns. Now, part of what's called the efficient market hypothesis assumes that all returns, all prices are identically distributed. They're independent of one another and they're identically distributed, meaning they're sampled from the same underlying distribution. It's a mathematical assumption that they make because if they don't make that, they don't have any other math. Again, back to what are we going to do? Well, we got to assume something. Let's assume this. Is it true? Most of the time. So right, in pure research, if you're correct 80% of the time, that's not publishable. Imagine if the theory of gravity only worked 80% of the time. Imagine if your computer only turned on 80% of the time. No one's buying this stuff, right? That's not, you don't know what you're doing. But somehow here it flies. Okay, so fine. So you've got this assumption of independence and identically distributed returns. And yet we see that there are correlations between a fund's own returns, meaning March's return is correlated to February's return is correlated to January's. And so if you take the entire return stream of a particular fund and you calculate the correlation of it against itself shifted by 1 month, the answer should be 0, no correlation. The answer in reality is about 0.2. That's measurable. That's not 0.2 plus or minus 0.5. That's 0.2 plus or minus like 0.05. So you know it's not 0. And if you do that for multiple shifts and you're constantly getting a high correlation, you know something's going on. So he studied what's going on. And he said there are a couple of sources of this, legitimate sources. One of them is you're invested in illiquid securities. So if you're invested in securities that themselves don't trade very often, and a lot of fixed income funds were doing that, leading into the global financial crisis, then you're going to manifest this kind of friction in your returns. Okay, that's a source of risk. We can measure that. Fine. And he measured, and he identified the 4 or 5 legitimate things. And then he said, the single biggest effect, though, is cooking the books. You made a lot of money in January. You made 10% in January. You know you're not going to make that in February because you're posting your returns on February 10th. You already know February is a crap month. So you know what? We didn't really make 10%. We made 6. Now I've got 4% that I can hold in reserve and buffer my February returns from. So, okay, so that's a way to distribute the returns across different months. That's illegal. You're not allowed to do that.
Bernie Madoff, infamously.
Okay, that's where I'm headed. It's exactly where I'm headed. He came up with a very simple Madoff detector that we then built into our system. And we were going to publish it. We were going to go out, and Madoff collapsed 2 months before we published. And we tested on Madoff, and Madoff was actually one of the ones we said, holy shit, look at this. Now, he was claiming to trade equities and options, two of the most highly liquid securities. So there's no way that there's friction because of the illiquidity of the securities he's trading. This is all cooked books. Now, we also found a couple of other funds that had similar characteristics. And one of our clients they knew we were working on this. They brought it to us and said, hey, can you test on this? And we said, yeah, there's something fishy going on here. That was a hedge fund who actually came clean. And he said, I got duped. It was a hedge fund manager who went back to his investors and said, I invested in a security that turned out to be fraudulent.
Okay. Was it a security or was it a fund-to-fund situation?
It was a structured finance security. It was one security. It was a custom structured finance. It was like one of these CDO squares or CDO cubed. It was one security. He was the only investor, and he got completely snowed. And he made good. I mean, good on him. He went back to his investors. He said, this is coming out of my fees, not out of yours, and went on, right? But that's risk. That's risk. Okay. Volatility is not risk. Risk is, we were talking off camera before about the NASDAQ was down 23%, right, in 1987. 23% down in one day. That's risk. That's catastrophic wealth eliminating risk. 2%, one standard deviation, 2%, two standard deviations, three standard deviations, that's normal.
So you mentioned the great financial crisis a few times. So, and this occurred while you were still running investor analytics.
Yeah.
Across securities, commodities, public real estate, there was a very, very large drawdown, meaning a lot of asset prices fell. On top of that, you had some major companies go bankrupt. Lehman Brothers was probably the most infamous. You had Washington Mutual as well, which was a pretty large bank. For someone that models risk, what was it like to work through one of the most volatile financial crises on record?
So I'll start by saying, because we were the hedge fund space, hedge funds in good times and in normal times go out of business there's a high default rate, if you will, or out of business rate. We lost over 60% of our revenue.
Wow.
Through the global financial crisis. So it was, from a running a business perspective, it was incredibly, incredibly challenging, right? But let me rewind. So about a year before the crisis was full on hitting everybody, we had a number of Swiss banks as clients. Now, at the time, Swiss banks had proprietary trading desks that effectively were internal hedge funds. So they would trade all manner, multi-strat, all manner of different types of securities, different strategies, different asset classes, et cetera. And one day, one of our Swiss clients, now I love doing business with the Swiss. I really do. They're very clear. They're very transparent. This is what we need. This is what we want. Do you offer this? Okay, let me see this. Let me see that. You don't do this. You don't do this. We won't do business with you. Clarity. It was wonderful. Oh, you do this. I'm looking for this. Can you adapt your system to this? You can't. Okay, we'll do business with you. Clarity was wonderful. Okay. So here I am. I get an email, a phone call, whatever it was, from one of our Swiss clients, sophisticated trader, calling and saying, Damian, your risk numbers, they're going through the roof. What's going on? I might have to report this to the vice president. Specific question. Why are your risk models wrong? Interesting. What makes you say our models are wrong? Well, Risk Metrics are a massive competitor, spun out of JP Morgan, much better, much more well-known than we were. Their models aren't showing any deviation. Their models are saying the risk today is the same as the risk yesterday, is the same as the risk before. What's wrong with your models? Okay, first of all, I don't know their models. I don't work there. I can tell you what our models do. We finally figured out the difference because we were like, and this is one of the most painful parts of running this business was justifying our models compared to other people's models. all models are wrong. Some models are useful. I have no idea who said that. Probably 100 different people, right? Everyone knows the quote. It's absolutely true. Mm-hmm. Here was the fundamental crux of it. Our models were fast-moving models, exponentially weighted, meaning you overweight recent information, you underweight older information. Our models had an exponential curve, looked at the last 100 trading days, that's half a year's worth of, a little bit less than half, it's 5 months worth of trading. And we weighted it so that half the weight was in the last 2 weeks. So short-term memory model. Okay. Our competitor used a 3-year flat-weighted model.
Interesting.
So yesterday was as important as 3 years ago, the market movements. So our model is picking up something in the interest rate markets, credit markets. The credit spreads were widening, right? The markets were saying something's not kosher. Our models were picking that up. Their models were not.
And credit spreads is the difference between higher rated credited bonds versus lower rated credit or lower rated bonds.
Yeah, very simply, you can think of it as the difference between a corporate bond and a government bond, right? It's the spread, the difference between what you have to pay, because like the U.S. government risk-free, right? We've learned that not all governments are risk-free, right? It used
Argentina,
Greece. Yeah. I mean, we've learned some pretty big economies, right? Anyway, yes. So credit spreads were widening, more risk. Our models were picking it up. Their models were not. And it took like a month or two to figure this stuff out, right? So here we are watching not only the financial markets collapse, we're also watching, at the time, the measure called value at risk. We still use it today. Value at risk was blamed as a poor tool because it didn't predict the financial crisis. And I can't tell you how many journal articles I was interviewed for, how many TV spots I appeared in, how many times people said, well, didn't your model, isn't a failure of the models? I'm like, actually, no, not at all. It's a failure of the interpretation of the model. It's a failure of the assumptions going into it. Depends on how you build the model. If you use the Gaussian assumption, yes, it's a failure of the model. Absolutely. The non-Gaussian models did actually pretty well. Our model, our fast-moving model, picked stuff up pretty quickly, right? It's all about interpretation. And I said, look, it's blaming the method in the global financial way, blaming the model is kind of like saying, well, the stethoscope didn't pick up that I have cancer. Nope, it didn't, and it won't ever. So it's the wrong tool to measure the wrong thing, right?
Yeah.
But when money is flowing, people look the other way, and they don't pay attention to that level of detail. So that's what it was like going through the global financial crisis.
Yeah, and we'll talk about, I guess, the risk of money flowing in the present day.
Yeah.
But before that, I heard this story from somebody that my understanding is that you knew someone who claims they came up with a similar model to the Black-Scholes Merton model, which is it's used to price European style options. And it was Fisher Black, Myron Scholes, Robert C. Merton. They came up with this model. So can you tell us the full story about this?
There actually are two different stories.
Okay.
In a similar vein. I'll tell them both quickly. So before Merton was involved, so one of the guys that I found investor analytics with, economist who was he was trained as an economist at that time. In '68, he was at Chicago, University of Chicago. He was on the faculty. He since went on to be the chief financial officer of Chase, chief risk officer of Chase. He went on to become CEO of UBS Asset Management. So he had a storied Wall Street career, but rewind back to late 60s, early 70s. Fisher Black was at Chicago. Fisher walks into my partners, Dick Zecker. He walks into Dick's office and he says, Dick, I'm working on I'm trying to figure out what an option might be worth. And he writes out half of the differential equation, which became the equation that he and Myron Scholes ultimately solved. And he asked Dick, can you help me? I'm struggling with this part. And Dick, as Dick told the story, said, nobody was interested in options. Options, every economist worth his or her salt at the time was saying the gold standard. Everyone was working on the gold standard. That was the thing that anyone, if you want to get tenure, work on the gold standard. So he literally said, Fisher, what the F is an option and who gives up? And he said, you know what? I know who might be interested in this. And he introduced Fisher Black to Myron Scholes.
Okay.
So as Dick told me, he said a Nobel Prize walked into his office on a silver platter and he kicked it out. So that's story number one. Story number two, very good friend of mine, his father, mathematics professor here in New Jersey, solved the Black-Scholes equation around the same time, maybe a little bit before Black and Scholes published their equation. Now, I believe this to be true for a couple of reasons. One, anybody with a good mathematics background can set up and solve that equation. It's a second-order differential equation. It's the same equation as heat transfer in 2 dimensions. When I studied the paper that they published, Black and Scholes, my biggest challenge was translating the notation from economics differential equations to physics differential equations, because things like a dot over the x in physics means a time derivative. In economics, it means some other type of derivative, or maybe it means an integral. So you can get very confused very quickly. So that was my challenge in translating it. But his dad solved the equation numerically, not closed form, and he traded against it.
Okay. Now, so at least he made some money off of it.
And so one thing that hedge funds taught me was nobody really tells you what they've solved if they've actually solved it. They just go use it to make money.
Yeah.
And so I didn't learn that this guy solved it until I was telling him about the first story that I just told you about, the Nobel Prize being kicked out of the office. So he didn't tell anybody he solved it. He never published it. He just quietly made his money.
Yeah.
So that's why I believe him.
Good for him. And kind of you see that a lot where people claim to generate what people in finance call alpha, which are returns over the market. A lot of times people compare themselves to the S&P 500, but usually the people that are generating alpha, they're doing some very interesting strategies, and they're at Citadel or Millennium, where you as a retail investor just wouldn't be able to do anything close to that.
No, you can't. You can't. Look, they've got algorithms trading, and high frequency traders are trading in milliseconds, microseconds. Some of these people actually bought real estate. They bought offices across the street from the New York Stock Exchange, putting fiber in so that they could save nanoseconds. I'm not kidding.
Do you have Flash Boys in your book?
It's not in this pile, but yeah, it's certainly worth a read.
Yeah, it's kind of talking about what you're explaining now in terms of getting very, very close to the financial markets in New York, so physically.
Yeah, because look, it takes time for the signals to travel, right? Electric signals travel. A nanosecond is about a foot, right? So, this stuff adds up, right? And if I can front you by a microsecond, I can trade against you all day long, making a lot of money.
Yep. Yeah. All right. Let us go to the present. You still conduct risk analytics within finance. Right now, we are in late 2005 going into 2026. Buzzword is AI.
Yeah.
NVIDIA is a $5 trillion company last I checked, and tech stocks from Google to Microsoft and it's soaring. So I got out of finance because I think it's a really complex model. I have not figured out how to achieve returns above the market. So I buy the market, and I'm fine with that.
Uh-huh.
And it's natural to project what will happen in the future. Working in the tech field, I am skeptical of large language models and that they'll be as disruptive as some of the most optimistic people think they will be.
Right.
So to bring this to the fundamental finance side, the amount of capital expenditure that is going into, just in general, into the field is pretty large. What risks do you see right now, if any?
So first, I'll say I have not really been in the markets as much since I sold my company in 2016. For the last 10 years, I've pivoted to being a financial software executive. So I now manage teams that build and build software for analytical purposes, one of which is risk, not only risk. Okay, so I've been out of the hedge fund thinking mode for a decade. That said, I didn't just go through the financial crisis. I started the company in 99. The tech bubble burst a year later, 9 months later, after we started the company. Large language models. Look, we've been working on AI since the 50s, 60s. Large language models are the first massively useful application of AI. The irrational exuberance, to quote Greenspan. Do you know that quote?
Yes.
It was from the global financial crisis.
Yeah.
Irrational exuberance. Irrational exuberance defines the markets. Okay. So we haven't yet talked about behavioral economics.
We can also tie that in if you want.
It's absolutely tied into this. That's why I bring it up. It's so everybody, right? JP Morgan famously, when JP Morgan's shoe shine boy asked him what stocks to invest in or something about the markets, he left and he immediately started shorting stuff. Because if my shoe shine boy is asking about the markets, it's a bubble. Okay. Everybody who touches a computer these days knows about AI. Not everyone's actively using it, but a lot of us are.
Yep.
About the only direct, really beneficial application that I see for AI today is in coding. Helping developers be much more efficient, helping non-coders code. It can sift through data if you know how to ask the right questions. So it's helping scientists who know how to ask the right questions. It's helping them sift through data. I agree with you. I don't think it has the potential that a lot of people assume it does. I could be wrong.
Yeah.
But I don't think it does. What I do know is that an enormous amount of money is being spent by the market dominant companies. So the concentration in the S&P, the concentration in the NASDAQ, the concentration in the major, because the markets are cap weighted, because the indices are cap weighted, capital weighted, meaning the biggest companies outweigh. You don't just take the price and you average the price across all the companies. You weight it by the size of the company.
Yep.
So the top companies have been overweighting the S&P for the better part of a decade. Maybe it's been 7 years, but it's been a while. Google, Microsoft, Meta, Facebook, Alphabet, parent companies, yeah. NVIDIA, they are spending an enormous amount of money building infrastructure for the supply that they anticipate will be needed to meet the demand that hasn't yet materialized. What a lot of people forget is that the tech bubble was not a whole bunch of internet startups that went bust. I mean, it was, but that's not the part that mattered. What mattered was the massive overspending by the telecoms in laying down the fiber and the internet cables. We had ISDN, we had dial-up in 99, and they were putting in fiber, anticipating that everybody's going to have high-speed internet in their homes in 1 year, 2 years, 3 years. A lot of that cable that got laid is unused, still buried under the ground, because the companies that laid them went bust. So knowing how much to invest in the infrastructure for the demand is critical for long-term success. Short-term success by our stock market is showing that you've got an enormous revenue. Now, the whole game of, okay, I got a lot of cash, so I'm going to loan you money to buy my products. which is going on rapidly.
Yeah, infamously, NVIDIA is right part of this loop of investing in companies that they're dealing with.
And you've got so Microsoft, for example, is Meta, is Alphabet, are they software companies or are they becoming hardware companies? Because they are investing in the infrastructure. Now, it's worse than that, right? Because look, software can be modified in minutes. In realistic terms, it takes weeks. Right? If you have to do the hot patch, maybe you get your best team working overnight, 3 days or something. But it's measured in short terms where you can actually change stuff. Okay. The chips, the NVIDIA chips that are being shipped today are going to be replaced within a year or two by the next gen chips. The infrastructure in the factories or in the data centers that are being built, not factories, the data centers that are being built to spec for this generation chip. How much cooling, how much space do you need, how many how many can you put in this physical space? And those data centers, it takes years to build them. So it takes years to build the physical infrastructure to spec on something that hardware is going to be replaced in a year or two. Add to that the fact that, from an accounting perspective, on the books of the people investing in this stuff and and buying this stuff, so the depreciation schedule for hardware, I always use 3 years. I'm going to have to buy a new server in 3 years. So it's effectively, its useful life is about 3 years. Now, I might still run that server for another year or two to do other stuff, but not for the production stuff that I need to generate my revenue. They're extending it out 5 years, 6 years. So hang on a second. The chip that's going to be replaced next year, from an accounting perspective, I'm saying I only have to depreciate, meaning my expenses. I'm pretending pretend is the wrong word. My accountants are saying I'm allowed to say only 1/6 of that expense is taken this year because I'm going to be expensing it for the next 6 years. But next year, I'm buying brand new chips, and I can't put it in my data center because the cooling requirements are for the previous chip. You know what? I smell 1999 all over it.
Yeah, it definitely seems that way. And it's like the depreciation of the graphical processing units.
Yep.
The GPUs is what you're talking about. It's one of the many risks that I think that there are. And yeah, it'll be interesting to see a year or two down the line if this is going to keep going up or if we'll have some sort of the re-rating of the stocks themselves.
Now, here's the thing that I think here's where the risk really comes in. A lot of people got caught with their pants down in 99 and 2000 because they expected warning bells. I'll get out once I see these warning bells. Here's the problem with that approach. This stuff can collapse in hours. From a behavioral economics perspective, perception is what drives the market. Perception. Based on numbers that we've got in reports. I'm not waiting for alarm bells because I think the alarm bells come after the fire has already consumed the building.
Yep.
And that's that. So I'm not going to say whether I'm long or short AI because I'm not giving financial advice. I don't know when this bubble is going to burst. I don't know if it's a massive bubble or a tiny bubble. I would just say if you're expecting alarm bells, history does not support that approach.
Yeah. So only time will tell. It will be interesting. So the final topic I want to talk about is the intersection of physics and finance. So we spoke earlier about the Black-Scholes model, and you mentioned it was a variation of the heat equation.
Yep.
I know when I was studying finance, I also learned about Brownian motion, which is used to model the random movement of asset prices over time. In physics, Brownian motion is used to model the random movement of particles suspended in liquid or gas. So is there something fundamental that ties together finance and physics?
That brilliant question. So here's the short version of the answer to that. the math that physicists used, I'm going to say the maths, plural. I'm an American. I don't mean British maths. I mean the different types of mathematics, plural, that were invented, plural, over the years to solve different physics problems. Newton and Leibniz invented calculus, invented it. They came up with the methods of calculus to solve very specific problems. Ballistic balls, moon around the earth, gravity, very specific problems. And it worked brilliantly. Holy crap, awesome. Fast forward, Maxwell came up with equations about electricity, differential equations, to solve that particular problem. Again, brilliant application of differential equations to a physical system which behaved according to the math, had to modify stuff. Then they came up with, wait a minute, gases. Gases, we can't use differential equations. They couldn't figure it out. They could have approximately figured it out with differential equations. They would have gotten about 60%, 70% correct, about as well as economists understand the economy. They could have. They said, we need a different type of math. And they invented statistics, statistical mechanics. They invented statistics, but they really propelled statistics in understanding. And now we have measures like temperature. You don't know the velocity of every single molecule moving around, but we know the temperature. And the temperature dictates the distribution of both. And so you come up with macro measures to understand without trying to understand the micro, because you can't understand that. And you've got a different approach. Okay, now we understand that. Quantum mechanics came about. We had to throw that out. No, we didn't throw it out. It's still applicable to statistical mechanics are still applicable to classical systems, but now we have quantum mechanics. Had to invent a completely new type of math. It's that group theory is used in high energy physics to understand the symmetries of particles. And so physicists and mathematicians have invented new math to solve the physics problems as the ages went on. Economists took the success of differential equations and applied it to markets, to the economy, and continue applying that same technique despite the fact that it doesn't work. In the late 80s, I think it was the late 80s, Murray Gell-Mann, Nobel Prize-winning physicist, started a phenomenal institute called the Santa Fe Institute. He got together some brilliant minds in physics, brilliant minds in economics for 2 weeks to try to work together to figure stuff out. And they walked away with a couple of things. The economists said, holy crow, those physicists are really full of themselves. They think they understand everything. The physicists walked away saying, oh my God, the economists don't understand a damn thing about economics. Neither do we, but they make assumptions that they're just wrong. Fast forward. Markets and the economy are used the word complex before. It's a complex adaptive system, and these means very specific things. Feedback loops, nonlinear feedback loops, where decisions made by one pocket will influence another pocket, and there's a nonlinear effect back to the first pocket, and we have multiple pockets, right? The analogy that I like a lot is you live in a house or in a dorm room, or you share living quarters with other people. You have one hot water heater. We have one water heater and your local showers. 2 people are in the shower at the same time. You're fighting about, right? That's feedback. I want hot water. Oh, now it's too cold. Now it's too cold, right? And that's a simple feedback system. Bee swarms are another feedback system. You've got behavior at a micro level that manifests itself as behavior at a macro level that is unpredictable. Biology, evolution follows this. So, and what I used to say when people ask me, so why did you go to finance? Why did you stay in physics? I said, frankly, finance is harder.
Yeah.
And I said, imagine how much more difficult physics would be if protons had personalities. Every proton behaves exactly the same as every other proton. I don't know if any two human beings would behave exactly the same. Right. So the markets are made up by individual humans who have biases and behavioral economics and all of those things that go into how the market perceives things. And yet we're trying to apply 300-year-old mathematics that is brilliant to solve that problem over there. But we're trying to apply it over here. And we keep trying to apply the same thing to it, and it's not working. Now, I don't mean to say that it doesn't work at all. It works well enough that we're going to keep trying at it. Unfortunately, the best answer that I have is it's so complex that we don't have a good grapple. We don't have a good understanding of the fundamental principles. Back to Andrew Lowe's 9 to 9 laws that explain 3% of what we see. So there is a connection because smart people like to work on hard problems, and they're working on both of these problems. There are some tools over there that have been applied over there. Some people make, and in pockets you can make a lot of money at it, but as a global macro system, understanding how it works, so that has direct implications to policy and market dynamics and how not just we invest individually, but how the system works.
Yeah. So it's funny because what attracted you to finance kind of repelled me away from it because I took it as like, oh, this is too complex. I don't know. I could be working in finance at 20, 30 years and I can't really understand and have a generalized overview of what's going on. So,
but Adrian, so 10 years ago, I sold that company. For the last 10 years, I've been an executive at a couple of different software firms. So I'm also not in that. And
fair.
Frankly, for very similar reasons, we're not going to solve this problem in the short term. It's a hard, thorny, nasty problem. So I used to be a member of the Santa Fe Institute's business consortium back when I had this company. And that, I think, that approach has some real legs to really figuring this stuff out. But we're at the beginning stages of this. And here's the bias. We think we actually know a lot more than, we think we know more than we do. That's the problem. And everybody in the world is affected by this, right? Everybody needs money to do anything in life. So we all have skin in the game.
Yeah. I am hoping, because I actually only recently heard of the Santa Fe Institute, but I am hoping to interview somebody there because complex systems also fascinate me. And even though I don't work in finance, it still fascinates me. So.
It's a beautiful adaptation and application. Geoffrey West is a physicist there who wrote a recent study, the last 5 years. He published a book about cities where he applied physics thinking to the dynamics of cities and started with even biological systems. And it's amazing the symmetries that you get and the patterns that you get coming out of how cities work. Now, that's a microcosm of how the economy works. And so they're onto something there.
Yeah. Really interesting. So now let's get into the final questions. For any students that want to get to either the hard sciences or quantitative finance, do you have any recommendations?
Sure. So, this is going to sound like a turnoff, and I don't mean it to be. One of the things that turned me off of physics was a professor said, the privilege of being a physicist is that you get to choose which 23 hours of the day you want to work. Okay. That's not really true, obviously. But the sciences demand a devotion for success, for impact. You can have a career not doing this, but if you want to make an impact in the sciences, you got to understand that the motivation of the people who you are competing with, and you are competing with people, is not financial. It is purity of thought and success. It's intellectual success. Money doesn't matter to your competition. So if money matters to you, you are not as competitive. Money mattered to me. I was not going to be as competitive. And that's one of the reasons I left. That said, the sciences, I will say, learn from everybody you can. Study the people who do things successfully and spend the time. If you enjoy spending the time reading and doing the science, it's a great career path. It's a brilliant exercise. If you don't enjoy doing it, consider something else. I'll tell you one story that I had from undergrad. A professor gave me a very bad grade on a test because I reduced the problem down to a differential equation. And I said, the rest is just math. It's just math. I solved the physics. I set it up. The rest is just math. I went to his office to complain. I mean, I don't deserve a D. So, okay, let's solve your equation. It took me a long time to solve the equation in front of him, but he made me do it. Okay, I got it. It was okay. Now, if you, and the problem was a sphere and a test particle, what's the electric field that the particle feels at any distance away from the sphere? Okay. Your solution, as you come closer and closer and closer to the sphere, as the distance comes closer to the radius of the sphere, what does your equation look like? Well, I had to work this out. And I said, oh, it looks just like the solution that we solved in class of a particle near an infinite plane. And I said, okay. Is that what the sphere looks like close enough? I said, yeah, if you get really, really close to the sphere, it looks flat. The Earth looks flat locally. And he's like, okay. Now, go far, 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 far away. As the distance goes to infinity, what does this look like? Oh, this looks like the same equation as we solved also in class of a point charge from another point charge. I said, is that what it looks like far enough away? I said, yes. He goes, okay. What have you learned? Well, clearly, getting down to that, you're not going to understand the dynamics of how your solution fits into the larger frame unless you do that. There's the same professor who advised me, he said, Damian, physics is not a spectator sport. You don't get to watch other people do physics. You're either doing it or you're not. So that's my advice. If you love doing it, friggin' do it. But if you don't love doing it, maybe it's something you want to appreciate but not do.
Okay.
For finance students, look, I got into finance not through the academic route. When I 1995 is when I went to Wall Street, and that's about when the first financial engineering programs were being started by physicists who went 10 years before me, who had done their thing on Wall Street and then started academic institutions to say, hey, we can teach people to do this. Quantitative finance is a hard field to go into today. You have to be good at quant, you have to be good at math, you have to be creative, and you have to be good at finance, and it's very competitive because everybody knows about it. I got in at a time, I slipped in as kind of the window was closing, if you will. So I would say quantitative finance, if that's what you love, go for it. There are lots of programs, but it's not an avant-garde thing anymore. It's if you want cutting edge avant-garde stuff and you're quantitative, I would say quantum computers. I would have said AI, but I'm not going to say that anymore. There is, and private equity, I think, has a better track record than quantitative finance. That's what I'm saying.
Last question. So you have a few books here. Not sure if you want to get to them all, but
I'll do them quickly.
Okay.
So they cover a whole bunch of things that we talked about. So this is in no particular. No, I'm going to start with the one that I think is no particular order. I'll start. All right. Mind of the Market, Michael Schumpeter. This is an application of behavioral economics and how psychology affects our ability to trade. I got a lot of really, really good talking points out of here when I was doing presentations about behavioral economics. So this is a fun, easy, easier. It's not easy. It's not an easy read. It's a fun read. This is the very first book that I read about risk, Against the Gods. In fact, I wrote a critique of the book that I tried to get published in Harvard Business Review. Bernstein would not allow it to be published. I met him afterwards. I have a signed copy of this. I met him afterwards, introduced myself. He goes, oh, yeah, he remembered me. And I said, do you agree with my criticism? Oh, absolutely, 100%. But I was trying to sell books, so I wasn't about to reply. Excellent book. Excellent book. It's a history. It's 25 years old at this point. It's the history of how humans have thought about risk over the centuries. This is my single most recommended book for anyone interested in the application of mathematics and physics thought to the markets. The Origin of Wealth is a play on words from The Origin of the Species. It is a tour de force of the misapplication of mathematics to the markets and what we can do about it. This is not an easy read. This is my favorite book on the topic, by far. All right. Nassim Taleb. Taleb's best book, I don't think his most famous book is Black Swan. I think his best book is Fooled by Randomness, his first book.
I agree.
I picked that up. Crikey, it was I don't even remember, 2002, 2004. I don't remember. It was my previous house, so I do know that. It was before 2000. It was before the global financial crisis. Excellent book. This one's a little bit repetitive to that. He's got a couple of other books, Skin in the Game. He's got Anti-Fragile. Anti-Fragile, I think, is also inspired. It's brilliant. It's really good stuff. So Taleb's stuff, I think, is absolutely worth reading. All right. Dan Kahneman. All right. You can see, just based on the number of stickies that I've put into here, how thoroughly I read this book. Dan Kahneman, if you don't know behavioral economics and Kahneman Tversky, go look them up. Dan Kahneman's stuff is brilliant. This book will change the way you see the world. So of these so far, the two that I recommend most are Beinhofer's Origin of Wealth and anything by Dan Kahneman or anything about Dan Kahneman's works. And then the last thing that I pulled off, I love Annie Duke. Annie Duke is a professional poker player turned hedge fund advisor, or maybe she was a hedge fund manager turned poker player. I'm not sure what the order is. Thinking in Bets is another one of her really good books. It's all about the application of statistics to decision making. And her claim to fame, I'll say, is revealing, or at least the thing that I think is most interesting is she points out that the quality of a decision is absolutely not based on the outcome of the decision. And one of the games she has people, she plays with people is think of your best decision you've ever made, think of the worst decision you've ever made. And inevitably, it's always based on what happened as a result of the decision. That is not how one should evaluate the decision, because you don't know the result when you made the decision. At the point in time, you had certain information. If you had to make that decision, if you could simulate 1,000 runs of the history of the world, is your decision good in more of them than in fewer of them? Not in the one that we live in, but in more of if you reran the events. Right. And we don't think that way. This is behavioral economics applied to the real world.
Yeah.
So that's my list of books.
Yeah. And I'm looking forward to Skin in the Game. Damian, thank you so much for coming on.
Adrian, this has been a blast. I hope you enjoy it. I hope the viewers enjoy it.
And I think this is going to be a very great episode. Thanks, everybody.
All right. Cheers.
I never said I was a victim of circumstance. I still belong. Don't get me wrong. You can speak your mind, but not on my time. They will tell you you can't sleep alone in a strange place. Then they'll tell you you can't sleep with somebody else. Oh, but sooner or later you'll sleep in your own space. Either way, it's okay, you'll wake up with yourself. I don't need you to worry for me, 'cause I'm alright. I don't want you to tell me it's time to come home. I don't care what you say anymore, this is my